Hi class. So in our 4.5 video, we are going to be working with simplifying radicals. So again, radicals are the things with this symbol right here. Looks like a check mark with like a roof after it or a ledge after it. So we call that the radical sign, right? Like this, a check mark with a roof. Okay, then the radicals that we have been working with up till now have been radicals that are square roots. But we are going to start looking at higher possible roots indicated by a number written here kind of right where the check mark is, and we call that the index. Now, one comment about that, when there is no index, we understand n to be 2. In other words, we understand it to be a square root, a second root. And then if it's not a square root, so square root is like the default, and when it's not a square root, we write the number in there for what root it is, and we call that number the index. So over here in number 1, we would say this has an index of 3, and we would think of it as a third root or a cube root. This one here, we would think of the index as 5. So we would think of that as a fifth root. And then here, where there's no index, we understand that that is a square root, or that your index is equal to 2. So simplifying radicals that are either square roots or higher, third roots or fifth roots, we do a similar process that we did when we simplified square roots, but instead of looking for groups of 2, we're looking for groups that are the same size as the index. So you can do this in one of 2 ways. I kind of do a mashup between the two, but notice how they both start out with factoring. So we kind of want to break up the numbers under the radicals into smaller factors and figure out how many like perfect squares or cubes or whatever the root is, right? Figure out how many of those may already be there so that we can just take the root, or we think of that as simplifying the radical, is when we take the roots of things that are perfect roots, and then things that are not perfect roots would stay in the radical. So I'm going to kind of do a combination of both methods 1 and 2. So in number 4, this one is a square root. The index here is 2 because there is no index. So because of that, we understand the index is 2. So that means I'm looking for perfect squares, if you will. Or you can think of that as groups of 2, right? Whatever the index is, we look for groups of that size because that would make them perfect squares, and then I could square root them. So with 50, I think of 50 as maybe 5 and 10, and then 10 I can break into 5 and 2. So when I'm thinking of 50, it's really 5 times 5 times 2. So I think of that as, okay, I have a group of 2. That means that's a perfect square. I have a perfect square of 5. Therefore, I can square root that and bring a 5 outside of the radical. But the 2 that had only 1, right? In other words, like if you don't have groups of 2, then those aren't perfect squares, and therefore you can't square root them. So they have to kind of stay under the radical sign. So this is sort of like saying the square root of 25, right? Because 5 times 5 is 25. The square root of 25 is 5, and I'm multiplying that by the square root of 2, which is the square root of 2. So this would be our final answer here. For number 5, I have an index of 3. So that means I'm going to be looking for perfect cubes, right? Because this is a cube root, or you can think of that as groups of 3. The index is a size of 3, so I'm looking for groups of 3 because that is, after all, what makes a perfect cube. So I'm going to start factoring 108. I can see that 2 easily goes into the number. So 2 goes into 10 5 times. It goes into 8 4 times. And then I know that 54 can also be divided by 2, and I get 27. Well, there's my perfect cube, right? 27 is a perfect cube, but I'm going to keep factoring. I can break that into 9 and 3, and then 9 can break into 3 and 3. So there's my group of 3, right? So if you're looking at your cube root, I've got 2 times 2 times 3 times 3 times 3, right? Those were the 5 factors that multiplied together to make 108. 2 times 2 times 3 times 3 times 3. So the 2 times 2, even though there's more than one, it is a group of 2, it's not enough to have a perfect cube. You would need a group of 3 to be able to take a perfect cube. So this number right here, that's the 27. I can take the cube root of 27. This would give me 1 cube root of 3 because there were 3. This is not quite enough to take a cube root because I only had 2 of the same factor. So that will have to stay under the radical sign. So I will take out my perfect cube root of 27, which is 3, and then I will multiply that by the cube root of course, 2 times 2 is 4. So that stays under the radical. I just kind of multiply them back together because there wasn't enough to take them out. So I have a 4 under my cube root sign. Why don't you guys try number 6 and 7? All right, so for number 6, you should have gotten 2 on the outside of the square root times the square root of 6. This is because 24 can factor into 3 factors of 2 and 1 factor of 3. So though I have 3 factors of 2, I'm only looking for groups of 2 because the index was 2. Right? So I'm looking for square roots or perfect squares. So this right here would be like my perfect square of 4. And then I'm left with a 6. And so the square root of 4 is 2. And then 6 doesn't have 2 identical factors. It has 2 different factors. So they just have to kind of stay under the radical. Now in number 7, it's a 4th root. So we are looking for groups of 4. So 80 can factor into 2 times 2 times 2 times 2 times 5. So 80 happens to have a perfect 4 in it, a perfect power of 4. So because you have this group of 4, you have a perfect power of 4, right? 2 times 2 times 2 times 2 is 16. The 4th root of 16 is just 2. So when you have a group the size that matches your index, you can take the root. You can take the 4th root of this group since you had 4 identical factors. That goes outside of the 4th root and it's a 2. And then we only had a single factor of 5 on the inside, so then that has to stay under our 4th root. Don't forget to write your index, by the way. Because if you forget to write the index, remember we understand that to be a square root, but this is a 4th root. So it's got to be 2 times the 4th root of 5. Moving down to number 8, we see that this is asking us to find the negative square root of 64. So that means that we want only the negative root. Now, it's important for us to note here that the square root of 64, there's actually 2 different square roots of 64, right? There could be either positive 8 or there could be negative 8 because either one of them, if you square them, equals 64. So when we are looking at a square root sign like this one, if there's no negative in front, we didn't really mention this earlier, but we're going to talk about this a little later. But like, for example, in number 4, when there's no sign in front, then we only want the positive root. And that is called the principal root. And is sort of the default, kind of like when there's no index, we want a square root. And if there's no sign, we want only the positive root. But in the event that we do want the negative root, then you will see like a negative sign out in front. So this answer here would have to be negative 8, the negative square root of 64. Now in number 9, we see a plus or minus in front, so that means we want both of the square roots, both the positive and the negative square roots. So we know that 81 breaks into 9 and 9, and of course n squared breaks into n and n. So we actually have a perfect square of both 9 and n. Or that is to say, we have 2 groups of 2. Groups that match the size of the index. So those are both perfect squares. So when they come out of the square root, there's actually nothing left inside. So this would be an answer with no radical left over, and it would just be plus or minus 9n. Now this one here, so again, there's no index, so we understand it's an index of 2. So remember, we're looking for groups of 2, or we're looking for perfect squares. This is a binomial factor, so remember the x plus 1 has to stay together. I can't split it up. So I'm going to think of it like this. This is the square root of x plus 1 times x plus 1 times x plus 1 times x plus 1, because that's what this power means. It means that you have 4 factors of x plus 1. And again, this is a square root, so we're looking for groups of 2 perfect squares. And again, I have 2 perfect square groups of 2. So again, nothing's going to be left in the radical because everything was a perfect square. And I can take out 2 square roots of x plus 1 from this pair and from this pair. I can basically square root both and take out the root. And these are being multiplied to each other. So the result of this square root would equal x plus 1 times x plus 1. And that is x plus 1 squared. So I want you to notice something here, that the final exponent that I ended up with, this one here, so I ended up with the base x plus 1 squared, that was a result of taking the power of x plus 1 that was originally under the radical sign and dividing it by the index. Because the power is telling you how many factors there are, right? It's the number of factors of x plus 1. It's saying you have 4 of them, right? 1, 2, 3, 4. And then this index is telling you how many should be in each group. So we want groups of 2. So you're basically saying take these 4 factors and divide them into groups of 2. That's division. So you could have found this by doing the power divided by the index. And that could have also been how we arrived at this answer of x plus 1 squared. So I'm going to write that here. So when you're working with variables like this, you can basically divide the power that's in the radical or under the radical by the index. So maybe in some of our future examples coming up, we can kind of use that little trend that we noticed. So in number 11, again, we have a index of 3. So we're going to be looking for groups of 3 or perfect cubes, so to speak. Now 8 is a perfect cube because you can break it into 4 and 2, and then 4 can break into 2 and 2. So this is equal to the cube root of 2 times 2 times 2 times n times n. So for this variable, there were only 2 of them, not enough to make a perfect cube or a group of 3. So both of these n's are going to have to stay under the cube root. So no point in dividing, right? Dividing power by the index, because when I do that, power divided by the index, it's less than 1. That means I can't pull out any n's. They're going to stay under the radical. So we'll just kind of leave them there. But for my number, for 8, I do have a perfect cube of 2, or a group of 3. So I can pull that out of the cube root. So that means I have basically the cube root of 8, if you will, which is 2, times the cube root of the stuff left inside, which was n squared. So that's our final answer for number 11. For number 12, now I'm taking the cube root of a negative, but that's okay, right? This is totally allowed because you can multiply 3 negatives together. In fact, that's what happened here. Negative 5 was multiplied to itself 3 times, right? Because when you do the first 2 negatives, you get positive 25. And then when I multiply that by the third negative 5, my result is negative 125. So because you can multiply 3 negatives together to get a negative, that means you can easily take the cube root of a negative. You just have to be aware that each factor was negative. So that's what we're dealing with here. We've got negative 5 3 times. Now I'm going to write this out the long way and then kind of apply what we learned earlier as well. So there's 9 factors of a, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That is what the exponent means. This is telling me that there are 9 factors of a. This index is telling me that I want to break them into groups of 3. So you take 9 factors, break them into groups of 3. That's basically 9 divided by 3. 9 divided by 3 leaves me with 3 perfect cubes, perfect cube roots of a. There's also the cube root of, or the perfect cube, I should say, of negative 5. So this is negative 125, the cube root of which is negative 5. This is a to the third, the cube root of which is a, and again that happened 2 more times. So this is another one where there's actually nothing left under the radical sign because everything made a perfect cube. Everything made a perfect group of 3. And so I can take out 1, negative 5, and then 3 factors of a. So that ends up equaling negative 5 times a to the third power. So again, I can see that if you take the power on the inside, which was 9, divide it by the index, which was 3, so that would have given me, so that would have been 9 divided by 3. That'll give you the final power on your variable after you simplify the radical. That's how you can simplify the radical. It's just power divided by index, just like we saw up here in number 10. Divide the power by the index, and that'll give you your final power of your variable after you reduce the radical. So my final answer was -5 times a to the third. So let's try that shortcut here in number 13. So I have an index of 2, because there's no index written. So then according to that rule, this would be x to the power of 2 divided by 2, right? Power divided by index, which is x to the first, which is x. And that would be the square root of x squared. And then for number 14, similarly, I have an index of 4 and a power of 4. So this would just be m to the power of 4 divided by 4, which is equal to m to the first power, or m. And if you think about it, that makes sense, because m times m times m times m, which is what m to the fourth is a perfect group of 4. So you fourth root it, you just end up with m. In 15, again, I can take the base of a. I can think of that as a to the 4 divided by 4, right? Power divided by index, and that would be a to the first. That's being multiplied to n to the power of 8 divided by the index of 4. So I'm taking power, dividing it by index, and so that's a to the first times n squared, or an squared would be our final answer for 15. Now for 16, we have numbers and variables. So for the 32, I'm going to remember that it can break into 5 factors of 2. So first it's 2 and 16, but then 16 is 2 and 8, but then 8 is 2 and 4, and then finally 4 is just 2 and 2. So you see 1, 2, 3, 4, 5 factors of 2. So 32 is a perfect power of 5. So maybe I'll write it out. Maybe I'll write this out the long way, just again to remind you why the division works. So 32 can be broken into 5 factors of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. X to the 5th would be 5 factors of x, and y to the 10th would be 10 factors of y. 1, 2, 3, 4, 5. That's group 1 times 1, 2, 3, 4, 5. That's group 2. I'm just showing you one more long example so you can see why this division works. So this is a 5th root, so we're looking for groups of 5. Perfect powers of 5, which would be 5 identical factors multiplied to each other. So x, it told us here there were 5 factors of x, right? That's what the power means. That's 5 factors of x. There are 10 factors of y. And I want to split that into groups of 5. So I'm basically saying take 10 and divide it by 5. And when you do that, you get 2. So this is another case where there's nothing left in under the radical sign, because everything makes a perfect group of 5 and can be simplified. So the 5th root of 5 2's, or the 5th root of 32, is just 2. The 5th root of 5 x's, or x to the 5th, is x. And then I have 2 perfect 5's of y, so I can take both of them out. And of course, we're just multiplying all these things together, right? Because that's multiplied to that and that and that. So this 5th root of all this stuff ends up equaling 2 times x times y, or 2xy squared. Now again, you could also say for the x, right, because it was to the first power, you could take the power of 5 and the index of 5 and just divide them. And that's how we also could have figured out it's x to the first. For the y, you can take the power of 10 and divide by the index of 5 to see that it will reduce down to y squared. So you can use that power divided by index as a shortcut. If you get stuck, you can always just write it out and see how many groups you have that are the size of the index. Why don't you guys try number 17? Okay, so for number 17, you should have ended up with -11 times a to the 3rd power times b to the 1st. It has to be negative because of the negative in front of the root. It wants only the negative root. And then the square root of 121 is 11. And then for the variables, we take the power which for A was 6 and divided by the index, so 6 over 2 is 3, and then B is 2 divided by 2 as well. Now for number 18, we have an index of 3, so we're looking for groups of 3. But it looks like with the y, if I do the division option where I take the power of 5 and divide by the index of 3, it's not going to equal a whole number. It ends up equaling like a fraction, like it has leftovers. So that means that it's not going to simplify evenly, and there's going to be some factors of y left over. So it might be helpful to write it all out for this one. So for 40, I can split that into 4 and 10. 10 can break into 2 and 5, and 4 can break into 2 and 2. So I basically have 3 2s and a 5. And then I had 3 A's, so that one does break nicely into a group of 3. And then I have 5 Y's. 1, 2, 3, 4, 5. So I can see if I'm looking for groups of 3, right, because my index is 3. So I want groups of 3. I have one perfect cube of 2, because that would have been 8, right? 8 times 5 is 40. One perfect cube of A, instead right here, right, it was 8 to the third. And I have one perfect cube of y sort of buried in there, right? You can think of this as y cubed times y squared, and that's kind of what this is saying. You have one perfect cube and then 2 out of 3. If I would have just had one more factor of y, I would have had 2 perfect cubes, but I didn't. I was short. So this y squared right here is going to have to stay under the cube root sign. And so is the 5. I only had one factor of 5 that was inside of 40, so the 5 and the y squared will have to stay under the cube root. But I can take out a 2, right? Perfect cube root of 8. I can take out an a, and I can take out one factor of y. Those things can all be on the outside of the cube root. So I get 2ay times the cube root of my leftovers, 5 times y squared. Why don't you guys try number 19? Okay, so hopefully you got x to the third times y squared. We get a 3 for our power of x by dividing 18 by 6, because 6 was our index, and we get a 2 for our power for y by dividing 12 by 6. So here we're using that rule because both 18 and 12 divided evenly by 6, and they were both greater than 6, so they divided into numbers that were greater than 1, so we just went ahead and divided them. And this is our final answer.